and some basic concepts. So, one natural question that must have arose in your mind yesterday was that how can we build these robots, or how do these robots work, right? So, a disclaimer is that I cannot teach everything within these 2 sessions, right? But what I can tell you now is what are the basic mathematical principles on which these robots are programmed. How do these robots work actually? So mainly, these robots will comprise of mechanisms, the structure, right? So these structures work in a certain way and they are modeled in a certain way. So that is what we are going to discuss today. So first of all, in order to understand anything, we have to first understand the basic terminology or basic vocabulary. Because see, when you go into any class, any place, there is a basic list of terms, right? Basic list of lingo, as they say. So what we are going to look now at will be the basic lingo of robotics. So if you look at a stationary robot, there are different parts of it. Then this is a joint, and so on and so forth. Okay. So what is a link? Link is a rigid part. What is a rigid part? A rigid part can be defined as something where if you take any pair of points within that part, they will always remain equidistant when this part is moving. Okay. In the case of soft robots, that thing doesn't hold. So we are not talking about that. Joints permit relative motion between the rigid bodies or between the links. So think about my hand, right? So this is one link, this is another link, and this elbow is a joint. So this elbow joint is allowing relative motion between this link and this link. There are 2 main types of joints. There are many joints, but as far as planar robots, we are mainly concerned about these 2 types of joints. The first type of joint is called as a prismatic joint. A prismatic joint will permit translatory motion between 2 links. Translatory motion. So you have seen this type of slides or X table. So this part can translate with respect to this part without rotation. This does not rotate relative to this. It only purely translates. So it's a prismatic joint. Prismatic joint. The other category of joint is called as a revolute joint. A revolute joint allows rotational motion, pure rotation between 2 links. So the elbow joint, what kind of joint is it? Is it a prismatic joint or a revolute joint?
Revolute and both.
Elbow.
Both.
Prismatic.
Both,
Who
sir.
say prismatic and why? So if you look at my arm, right?
Yes, sir.
Is it performing rotation with respect to this or translation?
Translation, sir.
No, it is performing rotation, right?
Oh, yes, sir.
See, this is rotating, isn't it?
Yes.
About this axis. Translation will be when this goes away, right? So, a revolute joint, see, where do you most commonly find revolute joint? One is elbow joint. You look at the door, right? If you open and close the door itself will rotate relative to the frame of the building, isn't it? It performs pure. So here there is a picture of a revolute joint, right? So in a robot, if you see here, are the types of you can say motions, relative motions that can happen because of a given joint. So if you think about a revolute joint, it allows for 1 degree of freedom. It allows for 1 degree of freedom. If you look at a universal joint, which we are not right now talking about, that will permit rotation about horizontal as well as vertical axis. So it will permit 2 degrees of freedom. Okay. So if there is something moving on this plane, for example, let us say, think about this whiteboard as one working space. Okay, working space. Now suppose I draw a point on this point. So this point, think about this point like an ant. You know an ant, an insect? So it is moving on this plane. This ant cannot go out of the plane. Right? So this ant can be located with respect to any fixed frame of reference using 2 types of motions. One is this x and this y, right? So it can basically, whatever motion it performs. For example, let us say it moves like this and it comes to this point. So this motion can be broken down into displacement along x-axis plus displacement along y-axis, right? So pure translation is happening, and there are 2 degrees of freedom, x and y. Now imagine that there are 2 ants. There are 2 ants. This is one ant, and this is another ant. Ant, not ant, right? 2 ants. Now, if they are moving independently, how many degrees of freedom are there? How many degrees of freedom are there for this ant? 2. How many degrees of freedom are there for this ant? 2. So what is the total degree of freedom of this system? 4. Because you need 4 numbers to specify how they are moving. Correct?
Yes.
Okay. But now imagine I join them using a rigid link. Okay? Just imagine. Don't try on real ant, poor ant, but just imagine in your mind, right? You join them. Okay? So this link cannot bend, it cannot extend.
It
The
cannot
length is
compress.
constant all the time. Now, how many degrees of freedom will be there for this?
2.
Huh? 3, right? So, actually, if you don't put this link, 2 degrees of freedom for this, 2 for this, so 4 minus this one constraint. Minus 1 this constraint, so net 3 degrees of freedom. And what are those 3 degrees of freedom? It can be translation along x, translation along y, and rotation in this about z axis, for example. Right? So that's what basically is the concept of degrees of freedom. Am I audible like this only? Yes, sir. Or do I need this? Okay, I don't like it. So if we are now just bring this ant out in the space. Instead of ant, think about a pigeon, a small pigeon, flying around, or a bee, honey bee, right? So how many degrees of freedom are there for the honey bee? 6 or 6. Honey bee is a point, right? Think about it as a point. That's why I said small. So 3, right? Translate in x, translate in y, and translate in z. 2 honeybees connected by a link.
3.
3 plus 3, 6, minus 1, 5. Right? So this way, if I give you any system, you should be able to find out the number of degrees of freedom. If there is a link, if you think about only my arm, how many degrees of freedom are there? Forget about me. Let's say I disappeared, only my arm is hanging in the space. How many degrees of freedom are there?
3.
There will be 6 degrees of freedom, because now it has a length also, right? It has a shape. It's not like a honeybee which is very small, right? It's kind of big relatively. So it can translate x, y, z and rotate about x-axis, about y-axis, and about z-axis. So net 6 degrees of freedom. Okay? So if 3-dimensional object is moving, then it has 6 degrees of freedom, and if something is moving on a plane, then it will have 3 degrees of freedom. Mechanisms can have two varieties in